So catalysts are any compound or material that either accelerates a reaction or allows a reaction to occur that wouldn't occur otherwise. And we depend on catalysts in our everyday lives for lots of reasons that we might not think about all the time. For example, any materials around us that are synthesized industrially are often made through catalysis. For example, plastics, synthetic fibers, dyes, detergents, pharmaceutical compounds, for example. And even the very atoms in our bodies ultimately come from catalytic reactions, because many of the nutrients that we take in our diets either come through industrial catalytic reactions or through naturally occurring catalytic reactions that happen in biology. So although all kinds of materials have been discovered to do catalytic reactions, nowadays a lot of the most advanced catalysts in industry rely on precious metals. And this is an issue in the context of sustainability, because precious metals are scarce and they're also not distributed evenly around the globe. And so this makes them both very expensive, but also their prices have become very volatile and subject to political factors. Also, precious metals tend to be heavier metals, and so they're inherently toxic to human beings. And so one of the challenges facing the community studying catalysis is how do we get earth-abundant materials that are not only more abundant, but cheaper and less toxic to exhibit some of that same chemical behavior that we typically associate with precious metals. So in my group, we basically take a two-pronged approach. One approach is that biology has already solved some of these problems for us. So the idea is that biological organisms couldn't have survived if they had to rely on precious metals. And so we look at a lot of cases where biology is doing catalysis with earth-abundant chemical elements, and our thinking is that if we can understand how biology is able to accomplish that, we can take some of those lessons and use them to design catalysts in the lab that we hope ultimately will have an impact on industrial chemical synthesis. The second approach we take is that even though some of these reactions relevant to catalysis with earth-abundant elements aren't as mature as they are with precious metals, nonetheless we know enough now that we can design new molecules through rational design that we can get to behave in the way that we'd like. And so one main focus in our group is to design new catalysts that we've invented and get them to catalyze reactions that typically require precious metals. And so we've had some success, although we still face some challenges regarding efficiency and versatility, but we're hoping that if we keep chipping away, we'll eventually get there.
Yes, so one of the reasons why we work with iron is because we are trying to replace catalysts that contain palladium. And one of the reasons why we want to do this is because palladium is not only expensive, it is also not mined in the United States. It's mined in parts of South Africa and parts of Russia. And the cost of palladium not only is expensive, it also fluctuates quite rapidly and drastically for the last 10 years. The amount of palladium we have available to us has been decreasing over the last couple of years. And that small amount of palladium that we have available to us is not, the majority of it is not used for chemistry. In fact, the majority of it is used for the automotive industry and partly electronics and jewelry. So only about 5% actually goes to chemistry. These are the reasons why we want to focus on making catalysts that contain iron instead of palladium.
So in biology, there are actually enzymes that are natural catalysts. And the responsibility of these enzymes is to suck up a really toxic gas in our atmosphere, nitrous oxide, which depletes the ozone. It's also a greenhouse gas. And this enzyme works as a catalyst and it gets rid of it out of our atmosphere. So my research goal is to hopefully mimic or create some type of a synthetic model that will be able to do this type of chemistry. So a lot of the atmosphere is actually made up of nitrogen gas. About 78% of our atmosphere is nitrogen. So a really cool experiment that I wanted to do, or that I did, was I had liquid nitrogen, which at negative 320 degrees Fahrenheit, it'll boil. So what happens is if you have boiling water and you dump that into liquid nitrogen, you can actually create a synthetic cloud. And what happens is the nitrogen evaporates even more quickly, so you have a bunch of nitrogen gas, and then the steam from the water actually condenses and it makes a really cool type of a indoor cloud. So the other really cool thing about liquid nitrogen is it's so cold that it'll take a lot of energy or heat out of the bonds between atoms. So normally when there's at room temperature, there's a bunch of heat and bonds will actually allow atoms to vibrate. But when you put them into liquid nitrogen, it's so cold that it literally makes them extremely rigid, and it takes all of that heat, all that energy out, and it makes them behave more like glass, where they're not as flexible, there isn't enough heat, and they actually shatter.
Okay, so when you take magnesium, which is a very flammable substance, and expose it to carbon dioxide, it reacts with the carbon dioxide and forms carbon and oxygen. When you create the oxygen, it creates more fuel for the magnesium, which makes it burn brighter. So if you put it with solid carbon dioxide, there's just more carbon dioxide around, so it makes it even brighter. So when you take metal salts, like sodium chloride, which is standard table salt, and put it in methanol and then start it on fire, it creates a certain color. And this color is based on the electrons in the actual atom itself, and it jumps up to a higher energy level and comes back down and emits a certain kind of light. But when you do this with other elements, it creates different kinds of energies and can create different kinds of light. All right, what's this one? Potassium. Potassium. Come on. What?
That's my favorite.
Maybe I'll go this way so the flame doesn't go towards me. All right. So suspenseful.